Hi Geometry, this is a review page of solving, graphing, and analyzing quadratic functions. This page is just to introduce us to each of the things that we're going to be reviewing the next couple class periods. So in our first box, it asks us to factor this quadratic equation to find the x-intercepts or solutions to the function. So my function is y equals or x equals x squared plus 4x minus 5. There are different methods to factor this. The one that I teach in class is to use this diamond method or x method. At the top of my x method, I put my c term, which is negative 5. At the bottom of my x, I put my b term, which is my 4. I'm getting those from the fact that a quadratic equation is ax squared plus bx plus c. So my c is my negative 5. And my b is my 4, and a in this case is 1 because there's no coefficient in front of the x. So I'm trying to look for two numbers that multiply to the number on top, while at the same time add to the problem on the number on the bottom. So as I'm thinking about the numbers that multiply to 5, really, I can only come up with 1 and 5. So let's see if I can make 1 and 5 multiply to a negative 5 but add to a positive 4. Well, that could happen if my 1 is negative. They're going to multiply to the negative 5, but they're going to add to the 4. So those are the two numbers that when I write this in factored form, it will be x minus 1, which is on the left side of my diamond, and x plus 5, which is the number on the right side. It doesn't matter which order you write this in, they're both correct. So either, in order for x minus 1 times x plus 5 to be 0, either the x minus 1 must equal 0, or the x plus 5 must equal 0. This is the zero product property from algebra. One of those two must be 0 in order for it to equal 0. So when I solve for x, I get x equals 1 and x equals negative 5. Those are my x-intercepts. They're called my solutions. They're called the roots of my equation. So if I plot x equals 1 and x equals negative 5 on this graph, 1, 2, 3, 4, 5, kind of hard to see on my iPad. I think that's negative 5. Those are the two places where my parabola is going to go across the x-axis. Those are my solutions. So what did the quadratic equation, the quadratic formula from last year help me find? Well, it helped me find that 1 and that 5. Not all functions are factorable. If they are, usually that's a quick, easy process. But the quadratic formula always works for any quadratic equation, even if it's not factorable. So let's see how it works in this one. This was x squared plus 4x minus 5 equals 0. So for my quadratic formula, I need my a, my b, and my c terms. So again, looking in front of my x coordinate, my a is 1 in this case, my b is a positive 4, and my c is a negative 5. I'm going to substitute those values into my quadratic formula. So x equals negative b, well that's negative 4, plus or minus the square root of, let's look at my formula, b squared, that's 4 squared, minus 4, now this is where kids have trouble. So the minus is in my formula, minus 4 times a, which is positive 1, times c, which is negative 5, and I'll come back to that in one moment, all divided by 2 times a. So in my case, 2 times 1. So let's simplify this radical a little bit, shall we? 4 squared is 16, and by PEMDAS, I have to do exponents first. Now be careful. If you look at the second part of my radical, that is a negative 4. Let the minus sign go with the 4. It's a negative 4 times a positive 1 times a negative 5. That gives me a plus 20 for my answer. If you looked at that as a positive 4, you can. That would give me minus a negative 20. Minus minus is still plus 20 underneath there. All over 2. And I ran out of room, so I'm going to go this way with it. So I'm getting x equals negative 4 plus or minus. Underneath the radical, I get 36. The square root of 36 is 6. So I'm going to write this as 6 all over 2. So this gives me two answers because of the plus and the minus. So I'm going to do both problems. Negative 4 plus the 6 gives me 2, and 2 over 2 equals 1. So that's one of my answers. And negative 4 minus 6 gives me a negative 10 over 2, which is where I get a negative 5. You'll notice those are the same answers I got in the first box because those are my x-intercepts. So what about solving by completing the square? So we had to use that method this year when we did circles, and you learned it last year when you did quadratics. So let's do that with this problem. Completing the square also always works, even if the problem's not factorable. So let's remember when I did circles, the first step was to move the constant to the other side. So I'm going to group my x squared together, my plus 4x together, and move the 5 to the other side. Now I'm going to complete my square. If you remember when we did circles, that was taking my b term 4, dividing by 2 and squaring it. In this case, it gives me 2 squared, that gives me 4. 4 is the number that completes my square. It creates a perfect square trinomial. But when I add it to the left side, I also have to add it to the right side. This is not like the 5. I am not moving it by doing the opposite operation. I am simply adding it to both sides. So now I'm ready to factor this. That's a perfect square trinomial. It factors into x plus 2 squared. I get the 2 from the middle step, or the square root of the first, square root of the third, sign from the middle, equals 9. And now I can solve this. We will be talking about this week, but to solve this equation, you had to take the square root of both sides to undo the x plus 2 being squared. And you got just x plus 2 because the square root and the square cancel, equals 3. I'm going to subtract 2, equals plus or minus 3. Last year when you did quadratics, 9 could be negative 3 times negative 3, or it could be 3 times 3. So now I'm going to subtract my 2 from both sides, and I'm going to just nestle it in front of my plus or minus 3. And now I'm going to do both operations. So it's negative 2 plus 3, which gives me a positive 1, and negative 2 minus 3, which gives me the negative 5. Those are the two answers I got using the method of factoring and the method of quadratic formula. So sometimes we use the discriminant, b squared minus 4ac, to tell us a little bit about my roots, which are my zeros, which are my solutions to my equation. It goes by all three of those terms. So if for this equation, I do my a, b, and c in my determinant, which is actually just what was underneath my quadratic formula, I get 4 squared minus 4 times 1 times negative 5. So I get 16. Again, this is a plus 20. Whether you think of it as negative 4 times 1 times negative 5, or 4 times 1 times negative 5 is negative 20, but it's a minus minus, it's positive. And I get 36. When you get a positive perfect square, that means I have two real, rational solutions. And that is proven to me 3 times already, because 1 and negative 5 are real rational numbers on the x-axis. So what else can I use here? Well, first of all, concavity, whether it's concave up or down. This one's up because the sign in front of my x squared term is positive. If it was negative, this would be concave down. Axis of symmetry. Oh, you know what? My axis of symmetry, I could use my negative b over 2a. This tells me the x coordinate of my vertex when I do this. So negative b, that is a negative 4, because b is 4, over 2 times a, which is 2 times 1. So I'm getting a negative 2. So the x coordinate of my vertex is negative 2. So if I go to negative 2 and do a dotted vertical line, that is my axis of symmetry. It is going to divide my parabola in half once I draw it. So how do I find my y coordinate? Well, let's plug my x coordinate into the equation. So I'm going to plug negative 2 in for x, and I'm going to see what I get for y. So this is negative 2 squared plus 4 times negative 2. I'm just substituting negative 2 in everywhere I see x. And that gives me 4 minus 8 minus 5, which gives me negative 9. So my y coordinate is negative 9. So let's go to negative 2, negative 9. This is going to be hard on these little lines for me. 1, 2, 3, 4, 5, 6, 7, 8, 9. I think this is -9. Your eyes, I'm sure, sees that much better than mine. I can sketch in my parabola. I'm going to do a soft sketch. It should not look like a V. It should look a little U-ish. It's kind of hard when it's stretched this much, but it should have like a little bit of a U look to it. Not too much of a V. It's not an absolute value function. So this parabola is pointed up. That makes its vertex a min. The y-intercept, so it looks like it might be here at 0, -5, but I don't really need to depend on that. I can simply, this is where I substitute in a 0 for x into the equation, and I find out what my y value is. So you can see up here, if I found my f of 0, I would get 0 squared plus 4 times 0 minus 5, so I would just get -5. So my y-intercept when x is 0 is -5. The number of zeros is the number of x-intercepts. We also call them solutions. We call them roots. There's 2 of them. And it was at x equals 1 and at x equals -5. The domain for parabolas, because this parabola is going to keep going off to infinity, all my x values are going to be used. So my domain is all real numbers, or from -infinity to infinity. Use parentheses, not brackets, because we can't contain infinity. And then to do range, I start at the bottom of my y-axis and I go up. And the first y value I encounter is -9. That's my minimum y value. And then I notice that my y values just increase forever. So again, that would be to infinity. So this is page 1 of our packet.